This section of the book is on integration by partial fractions. There are two main steps to solving integration problems using partial fractions. The first one is purely algebraic and can be used for other things other than integration. It's finding a partial fractions decomposition of the ratio of two polynomials. It's kind of algebraically intensive. It's not particularly hard. There are lots of steps, and in the end, you sometimes have to solve a ridiculous number of simultaneous linear equations. There are lots of computer programs that can handle this, some calculators. It's a kind of skill that you use on fairly easy problems, or you tackle fairly easy problems by hand, or not too bad ones, but if they're really massive, you would definitely give it to a computer or a calculator. That's the first part of the problem, is to apply this algebraic skill and find a partial fractions decomposition. Then we have to discuss how you actually integrate all the pieces that you get in the partial fractions decomposition. So what is a partial fractions decomposition? In high school, you should have done things like combine functions. So I want to start with kind of the reverse of the problem we're interested in, but just to show you where it might come from. Suppose you want to add these two functions. In high school, you should have seen that the first step is you get a common denominator. The common denominator would just be x plus 7 times x minus 2. And you want that same common denominator each place. So you'll multiply this fraction by x minus 2 over x minus 2, which doesn't change it. It just, right, because you're multiplying by 1, except when x is 2. So, and then this fraction, you multiply the numerator and denominator by x plus 7. And the whole point is that you now have a common denominator, and you can add the numerators now that the denominators are the same. And I'll expand these, so you get 3x minus 6 plus 5x plus 35 over, and I'll expand this denominator too. You get an x squared, you get a 7x, you get a minus 2x, and minus 14. And so what do we end up with? We end up with 8x plus 29 over x squared plus 5x minus 14. Great. You should have been able to do this kind of thing in high school. Add those two fractions and produce this. Our goal, though, in integration by partial fractions is to start with something like this and decompose it, find its partial fractions decomposition, figure out that we could write it as this sum. So the partial fractions decomposition for this you start with a problem that might be integrate 8x plus 29 over x squared plus 5x minus 14. We want to calculate this integral, and yet we don't know how to integrate this mess. And so what we do is we rewrite this fraction, and we want to undo what we did when we combine those two easier things, because if we could start with this and produce what we started with a minute ago, 3 over x plus 7 plus 5 over x minus 2, well, we can do both of these integrals, right? You get this. You can split this integral up as a sum. You can pull out the 3. You can pull out the 5. And easy substitutions of u equals x plus 7 and v, or call it u again, equals x minus 2 would tell you quickly that this integrates to 3 times the natural log of the absolute value of x plus 7 plus 5 times the natural log of the absolute value of x minus 2. But the question is, how do you start with this and recognize that it's this? This is called the partial fractions decomposition. You start with this and you produce that. So, of course, we know the answer in this case, but that's nice. Since we know the answer, why don't we start with this and talk about the general procedure for producing this? So, if we didn't know how to split that up, if we hadn't started with it in pieces and then combined them, how would we know what to do with 8x plus 29 over x squared plus 5x minus 14? Right? I don't have the integral sign. It's true we want to integrate the answer, but first we need to decompose this, find its partial fractions decomposition. There's a general statement of what a partial fractions decomposition is, and I will get to that. But first I want to look at 4 different examples that will make the general statement more clear. All right, so you start with this. How do you go about producing a partial fractions decomposition? The first thing that you notice is the degree of the numerator. The degree of the numerator, which is 1, degree of the numerator is strictly less than the degree of the denominator, which is 2. This is good. If this were not the case, the first thing we would have to do would be to long divide. If this were not the case, we would have to long divide polynomials. We'll do an example of this in a minute. But it is true that the numerator has smaller degree than the denominator, so we don't long divide. Or if we did, this is what we'd get. It doesn't go in there anytime, so this would be the remainder. So this is what you get. So then what do? You'd like to factor the denominator. Now we know how the denominator factors, but hopefully you could, even had we not started with the other problem, you could have looked at this denominator and said, yeah, I know how to factor polynomials. This factors is x plus 7 times x minus 2. And so we get this. However, it's not true that everything that factors over the real numbers factors with integer coefficients, or maybe you just didn't notice this one. What would you do in general if you wanted to factor this and you couldn't quickly see a factorization? Well, one thing you could do is completing the square. There are many algebraic techniques you learned of in high school that come up in finding partial fractions decompositions. So, in fact, completing the square doesn't help us a lot in this problem because we know that the denominator factors, but we will need this later, so let me go ahead and run through what would happen. If you have trouble finding a factorization, maybe it doesn't factor. How would you even know if it doesn't factor? You complete the square. So you would complete the square you would start with x squared plus 5x minus 14. We're going to complete the square. And what we get after completing the square will tell us whether the original thing factored or not. And if it doesn't factor, it will it'll tell us that it doesn't factor. And it'll leave this in a nice form that we want for continuing with partial fractions decompositions. How does completing the square go? You might think that this was difficult in high school, but it's really not. You want the leading coefficient to be a 1. If it were not a 1, factor out whatever it is, and then deal with what's in the parentheses that has a leading 1, and then just have that factor outside. But once the leading coefficient is a 1, completing the square is just adding 0 in a clever way. You take the x squared plus 5x, and you add and subtract the same thing. So that adds 0, but we do it in an extremely clever way. What's the clever way? You take half of the coefficient that's in front of the x term, so that's 5 halves, and you square that. So we add 5 halves squared, but we subtract 5 halves squared. Clearly that doesn't change our function. And then you put back in the minus 14. This may seem incredibly stupid. We just added 0. But we added 0 in a very clever way. What clever way? This part is now a perfect square. That's why it's called completing the square. This is x plus 5 halves, quantity squared, because when you square a quantity like this, you get this term squared, then you get 2 times this. So by putting 5 halves here, 2 times this is now 5x. And you get this squared, and there it is, 5 halves squared. So what are we left with? We are left with minus, this is 25 fourths. And we can go ahead and write this in fourths. This is minus 56 fourths. So what we get is that after completing the square is that this thing is x plus 5 halves squared minus 81 fourths, or what's the same thing, x plus 5 halves squared minus 9 halves squared. It's not so important that we got a perfect square of a rational number here. What is important, well, what determines whether this factors or not is whether we got something minus here, whether we got a negative number. This is something squared. If we had gotten plus 81 fourths, this would be irreducible over the real numbers. It would have no roots in the real numbers because it would be something squared plus something. That can never be 0. So it has no roots, so it doesn't factor, or it wouldn't factor. But we got something squared minus something. That does minus something positive. That means it does factor as the difference of squares, even if this were not a perfect square. Like if this were 7, if this whole quantity were 7, we'd think of that as the square root of 7 squared, and we'd still factor this as the difference of squares. So completing the square will tell you whether you have an irreducible quadratic term, so one that doesn't factor over the real numbers, or whether it does factor if you, and maybe you just didn't notice. So after you've got this factors as the difference of squares, and we better get what we got over there, but let's just verify it. You get the difference of squares. You get this plus this, so you get x plus 5 halves plus 9 halves times x plus 5 halves minus 9 halves. And then this is x plus 14 halves, but that's x plus 7. And this is x minus 4 halves, but that's x minus 2. So right, we got what we knew we would get. But in other cases, you might need to do this, and we will look at an example in a few minutes. Okay, so we're here. One way or the other, we're here. We looked at this, we said, okay, the degree of the numerator is less than the degree of the denominator. The denominator factors like this. Then a theorem tells you that this can be written uniquely. There are unique polynomials. There are unique polynomials that we can put here and here that will make this an equality of functions. So equal for all x that we're allowed to put in, so all x in the domain, which are all x's other than x equals 2 and x equals minus 7. And because this numerator has smaller degree than the denominator, these numerators have to have smaller degree than these denominators. But these denominators have degree 1. And the only thing of smaller degree would be either, well, 0 or a constant. other than 0, so a constant. The only polynomials of smaller degree than 1 would be constants. And so what we know is that there are constants that go up here. This is because there's a theorem that tells us they're unique polynomials, and that because this polynomial has smaller degree than this denominator, these polynomials have smaller degrees than their denominators. These denominators have degree 1, so the numerator has to have degree 0 or be the 0 polynomial. In any case, it has to be a constant. Well, we knew this because when we started with things that looked like this, we added them to get this, but assuming we didn't know it ahead of time, now we know it looks like this, and we'd like to determine that A and B are what we had when we started the section where we combined the two functions to get this in the first place. How do you do that? Well, at this point, you always do the same thing in partial fractions. You want to determine what these constants are. And so you clear the denominators. You multiply both sides of this equation by this big denominator on the left. So you multiply both sides of this equation by x plus 7 times x minus 2. Over here, what that gives you, the whole denominator gets wiped out. You're left with 8x plus 29 equals, over here, when you multiply this term by this denominator, the x plus 7's cancel, and you're left with a times x minus 2. Over here, when you multiply this term by this, the x minus 2's cancel, and you're left with b times x plus 7. There are unique a and b, constants a and b, so I should have written that these are constants. I said it, but right, these have to be constants. There are unique constants a and b that make this true. For all x that unequal to minus 7 and 2, things we couldn't put in up here. But why does, what I'd like to do is say this is true for all x, even though up here it only had to be true for all x unequal to minus 7 and 2. Why does it have to be true down here for all x? Well, a lot of people would say, well, both sides are defined for all x. That's not exactly why. Both of these are polynomial functions. Polynomials are defined and continuous everywhere. And so if we want these two polynomials to be equal for all x other than 2 and minus 7, they also have to be equal to each other when x is 2 and when x is minus 7. Why am I going on and on about, yeah, this needs to be true for all x, including the x's that we couldn't plug in up here? Because the nicest way to find a and b now are to plug in these exceptional x values, the ones that were zeros of the denominator up here that we weren't allowed to plug in. So this has to be true for all x. And what you could do at this stage is plug in any two x values you want. You get two equations and the two unknowns a and b, and you solve for a and b. And no matter what x's you plugged in, you'd find the same a and b. But there are two x's that you can plug in that give you a and b instantly without having to solve any equations. And those are exactly the x's you couldn't plug in up there. So if you let x be 2, this has to be true for all x. So in particular, it has to be true when x is 2. When x is 2, what does it tell you? It tells you that 16 plus 29 equals a times 0 plus b times 9. But that says that 45 equals 9b, so that b is 5. It immediately gives you b. We can also plug in x is minus 7. If we plug in x is minus 7, we get, so plug in x is minus 7 right here. We get minus 56 plus 29 equals, we're putting in minus 7, we get a times minus 9 plus b times 0. Okay, so we get, this is negative 27. We get negative 27 equals a times negative 9. So a is 3. So we find that b equals 5 and a equals 3. Of course we knew that. because it's what we started with. But this is how you would find it if you hadn't known, if you didn't know ahead of time. We get this is 3 and this is 5. All right, that's one way to find the A and B. I usually refer to this as the exceptional values method. You plug in exactly the zeros of the denominator that you started with, so exactly the roots of these linear terms that you factored, the exceptional values method. I also said that you could plug in any two x values and get two equations and two unknowns, A and B, and solve for A and B. And no matter what two x's you plug in, you'll get the same A. You'll get this A and this B. You'll get 3 and 5. There are no choices. There is one other method that you can use, and that's to use the fact that two polynomials are equal if and only if the coefficients in front of the corresponding powers of x are equal. So what we can do, and I refer to this as matching coefficients, you take the 8x plus 29 equals a times x minus 2. You don't need to do this one in addition to what we've already done. We already determined a and b. But some people prefer to do it like this. And in other problems, you have to do this at some stage. So you leave this side as 8x plus 29. You expand this side. So this is ax minus 2a plus bx plus 7b. You collect the powers of x. Here are the constant terms, the powers of x. So we get, this is a plus b times x. And then the constant term is minus 2a plus 7b. And this polynomial is supposed to equal this polynomial. But for two polynomials are equal if and only if their coefficients are the same. So we need the coefficient of x here to be the coefficient of x here. So a plus b has to be 8. And we need the constant term here to equal the constant term here. So minus 2a plus 7b needs to be 29. And then you solve these two equations simultaneously. There are lots of ways to solve simultaneous linear equations. One of them is multiply this top equation by 2, so we'll have a 2a and cancel with that minus 2a. So if you multiply the top equation by 2a, you get 2a plus 2b equals 16. We had minus 2a plus 7b equals 29. If you add these, the reference to a drops out. You get 9b equals 45. So again, we find that b is 5. Once you know b, you can use either one of these equations to get a. So for instance, once b is 5, a has to be 3 from this top equation. So plug this back in here, and you find, oh, so a has to be 3. We already knew that. All right, this is how partial fractions decomposition goes. And then, of course, we already discussed that if the problem is to integrate this, you now have to integrate these two things. You pull out the 3, you integrate 1 over x plus 7 with the easy substitution, u equals x plus 7. You add 5 plus, you integrate 1 over x minus 2 with the easy substitution, u equals x minus 2. It's easy to integrate. This is the easiest kind of partial fractions problem, where the denominator factors as a product of two degree 1 terms, two different degree 1 terms. And if you had a whole bunch of degree 1 terms, all different, then it's really not much more complicated than this. The exceptional values method is much faster then. You just plug in the different roots, and it gives you every single unknown constant immediately without having to solve any simultaneous linear equations. All right. Well, let's look at a harder example. I would like to, although not much harder at first, let's look at one where you start with the degree of the numerator being higher than the degree of the denominator. Okay, let's look at the integral of x cubed plus 2x squared minus 21x plus 71, all divided by the same denominator we had over there, x squared plus 5x minus 14 dx. Now this looks pretty horrible. This looks pretty horrible, but it's not so bad. But you should immediately notice that the degree of the numerator is greater than or equal to the degree of the denominator. It's 3, this is 2. You immediately long divide the polynomials. So I'll go through this because you may not remember, but so you take x squared plus 5x minus 14, and we want to divide this into x cubed plus 2x squared minus 21x plus 71. How do you do this? What you're supposed to do, it is really very important to have the powers of x decrease from left to right. Otherwise, you really may have trouble keeping things straight. And then, how many times does x squared go into x cubed? Answer is x times. And suppose I'll write that down here. Try to write it in line with the x's. It goes in x times. But then you take that x and multiply it times what you started with. So you get an x cubed plus 5x squared minus 14x. And this is subtracted. That whole quantity is subtracted. And so you get x cubed minus x cubed, that's 0. You get 2x squared minus 5x squared, so that's a minus 3x squared. You get minus 21x minus 14x, so that's plus 14x. Minus 21x plus 14x, that's minus 7x. And then you've just got this 71 that falls through. All right. And then it's, okay, how many times does x squared, so this x squared, how many times does that go into minus 3x squared? Minus 3 times. Minus 3. Then you multiply that back times the polynomial. So you get minus 3x squared minus 15x plus 42. And this is subtracted. So you get minus 3x squared minus 3x squared, that's 0. Minus 7x minus 15x, so minus 7x plus 15x, that's 8x. And then you get 71 minus 42, that's 29. And now this degree is smaller than this degree, so the long division stops. What may not have been emphasized for you in high school, maybe it was, maybe it wasn't, is kind of really, what does this tell you? Yes, we've just learned this polynomial goes into this polynomial x minus 3 times with this as a remainder. What does that mean? Well, what it means is that this quotient is equal to the functions. As functions, this equals x minus 3 plus, and then this is the remainder, plus 8x plus 29 divided by x squared plus 5x minus 14. That's what that long division tells you. That this quotient of polynomials, by the way, a quotient of polynomials like this is called a rational function, a quotient of polynomials. It tells us that this rational function equals this polynomial piece, so just x minus 3, plus this rational function. But now this rational function, after you finish long dividing, this rational function will have degree strictly less than the denominator. It has to be, because otherwise you'd continue with the long division. If this were an x squared, we'd divide some more and get an extra 8. And the long division produces a polynomial piece plus a piece where the numerator has strictly smaller degree than the denominator. And so we can use partial fractions on this. In fact, this is part of the partial fractions decomposition of this. There's a polynomial piece, and then you find the partial fractions decomposition of this. It is not a coincidence that this is what we had before. I did that deliberately so I could, at this point, save some work. So what do we get for the partial fractions decomposition of that? You have this polynomial part, and then you have what we had before, which is 3 over x plus 7 plus 5 over x minus 2. And that's the partial fractions decomposition of that rational function. And so you integrate it easily. You integrate this as a polynomial, so you get x squared over 2 minus 3x. And then you integrate these two pieces the way we just did a minute ago. So that's what you do if you start with a rational function where the numerator has degree that's greater than or equal to the degree of the denominator. All right, let's look at another example that isn't just some modification of our original example. Let's look at one that's completely different. As you can imagine, partial fractions problems can get very ugly. We haven't even looked at one yet where the denominator factors and one of the irreducible factors is an irreducible quadratic term. So a quadratic term with no real roots. But that's what we're about to look at. So let's look at the example. We want to integrate x plus 1 over x minus 5 times x squared plus 6x plus 11. All right. What do? You find the partial fractions decomposition of this. So it's already factored somewhat, which is good because nobody expects you to be able to factor an arbitrary cubic polynomial or higher degree polynomial. It's not easy typically. And so in these problems you kind of need to start with a factorization, or you could try to apply like the rational root theorem if you learn that and try to find factors. But generally, if you're expected to do this, you'll be given the denominator in a factored form if it's beyond quadratic. So we have this, and we would like to find its partial fractions decomposition. Okay, the numerator has smaller degree than the denominator, so we do not need to long divide. This is degree 3, right? The total degree. If you multiply this out, this has degree 3, this has degree 1, that's fine. We need to factor the denominator into degree 1 terms and irreducible degree 2 terms. So we need to factor this or complete the square. So it's not, I don't see any factorization of it. You should stare at it for like 10 seconds and think about factorizations. But hopefully you convince yourself fairly quickly that there's not one. And so you complete the square. Completing the square here means that you take the leading coefficient as a 1, so that's good. Means that you take this and you take half of the coefficient in front of the x, that's 3, and you square it, and that's what you add. But you immediately subtract it and put back the constant term that you had. So this is the same as x squared plus 6x plus 11. I added 9 and subtracted 9. It doesn't change it, but it makes it look different because this is now a perfect square. This is x plus 3, quantity squared. And then you've got plus 11 minus 9, so plus 2. It's a plus. This has no real roots. There is no real number that's root of this. It's something squared plus something. This will always be greater than or equal to, well, it'll always be greater than 0. In fact, it'll always be greater than or equal to 2. In particular, this has no roots. It can't factor again. So it's an irreducible quadratic term. And so we can stop trying to factor this. We're going to save this completing the square operation. We will use it again in the problem. But for right now, we just realize this is an irreducible quadratic and it can't factor anymore. What do we look for in the partial fractions decomposition? Well, you want to kind of undo finding a common denominator. And So we should look for something over x minus 5 plus something over x squared plus 6x plus 11. What should the somethings be? Well, it's just because this is a quotient of polynomials, and this polynomial has smaller degree than the denominators, they're unique polynomials that you can put here and here that'll make these equal, and these polynomials have to have smaller degrees than their denominators. So this again, this is a polynomial of degree 1. We need something of smaller degree. This needs to be a constant term. But here, this is a polynomial of degree 2. If all we know is that there's some polynomial of smaller degree that goes up there, well, then we should put the most general polynomial of degree 1 and see what b and c have to be. Maybe b will come out to be 0, and okay, we didn't need a polynomial of degree 1, a constant would work. But in general, b won't come out to be 0, and you just need to allow for the most general thing. So now our goal is to find a, b, and c that make these two functions equal as functions. So for all x values in the domain, which means, well, just this should be for all x unequal to 5, because this has no real roots. So that's what we want to do. How do you do this? Well, you do the same step we did before. You clear the denominators. You always do this. You want inequality of polynomials. So you always multiply by the big denominator on the left, the one you started with, to end up with polynomials everywhere. So you multiply by the big denominator on the left. And what do you get? So you take this equality and you multiply the whole thing by this denominator, which means on the left you're just left with x plus 1. Over here, when you multiply this term by this denominator, the x minus 5's cancel, and you're left with a times this quadratic. And when you multiply this term by this big denominator, the quadratic terms cancel, and you're left with the quantity bx plus c times the quantity x minus 5. So that's what we do. We have x plus 1 equals a times x squared plus 6x plus 11 plus bx plus c times x minus 5. Now, this is supposed to be true for all x. How can you find a, b, and c? Well, one thing you can do is you could plug in 3 different x values and get 3 equations and the 3 unknowns a, b, and c and solve for a, b, and c. We're not going to do that. In fact, I don't ever really like doing that. But another thing we could do is plug in exceptional values, the values for x that you weren't allowed to plug in before. Plug in roots of the original denominator. Oh, there's only one of those, so it's not going to give us a, b, and c, but it will give us a. If you plug in, this is supposed to be true for all x, in particular when x equals 5, which made the original denominator 0. But now we can plug in x equals 5, and you get 6 equals a times 25 plus 30 plus 11. And then when x is 5, this part's 0. So you get plus, well, it doesn't even matter, but a bx plus c times 0. So this part goes away, and you're just left with 6 equals a times, what is this, 55, 66. So a is 1/11, 6 over 66. So a is 1/11. Well, that was easy, but what about b and c? There are no other exceptional x values to plug in, zeros of the denominator. And for that, we are going to match coefficients. But it will be helpful to already have found that a is 1/11 with no real work, hardly any work, because we're going to multiply this out and collect the powers of x and then match the coefficients of the polynomials on both sides. So what do we get? We get x plus 1 equals, you get ax squared plus 6ax plus 11a plus, here, this times this, you get a bx squared, and then you get a cx and a minus 5bx, and then the constant term minus 5c. You get this, yuck. You collect the powers of x on the right. So x squared terms, here's one and here's one. So we get a plus b times x squared. X terms, there's an x term here, an x term here, and an x term here. So we get plus 6a plus c minus 5b times x. And then constant terms, those are the leftover ones. We get plus 11a minus 5c. And these coefficients on the right have to match the coefficients on the left. There is no x squared term on the left. There's no x squared term over here. That means that this has to be 0. A plus b has to be 0 because no x squared appears over there. So this must be 0. This has to be the coefficient of x that appears on the left. That's a 1. And this has to be the constant term that appears on the left. So this also has to be a 1. And so we get 3 equations and 3 unknowns. We get a plus b is 0, 6a minus 5b plus c equals 1, and 11a minus 5c equals 1. You know, it can be kind of ugly solving for 3 equations in 3 variables, but we already know that a is an 11th, is 1/11th. So really, knowing that, we only need 2 of the equations that we just found. So the 3 equations we just obtained were a plus b equals 0, 6a plus c minus 5b equals 1, and 11a minus 5c equals 1. But we already know a is an 11th. Well, that's nice. This immediately says b is minus a, so b is minus 1/11th. And then we could use either one of these equations, but this one looks the easiest to me. Plug in a as an 11th, you get, well, then this is 1. We get 1 minus 5c equals 1, so 5c equals 0, so c is 0. So we get this. So that's what we get. What does this tell us? It tells us that a is 1/11th, b is minus 1/11th, and c is 0. So in terms of our original fraction, ignoring for the moment that we care about integrating it, we want to find the partial fractions decomposition. We started with x plus 1 over x minus 5 times x squared plus 6x plus 11. We wrote this as a over x minus 5 plus bx plus c over x squared plus 6x plus 11. And what we just found is that a is 1/11th, b is minus 1/11th, and c is 0. So we don't need c, and b is minus 1/11th. All right. Now we're going up x. That was b. b times x. All right. So we have this. We might as well factor out the 1/11th just because it appears both places. This isn't really part of a general partial fractions thing, but you can, part of the procedure. But you might as well do that because it makes things look so much nicer. Factor out an 11th, we end up with this. Now I'm going to put in what we got from completing the square for this. It is x plus 3 quantity squared plus 2. We wanted to integrate this. It means we need to integrate this. Fine, we can pull out the 1/11. We know how to integrate this part. You make the substitution, u equals x minus 5, and this integrates to the natural log of the absolute value of x minus 5. But how do you integrate this part? And the answer is you add 0 in a clever way. In the clever way now, and really it's part of a general process that I'll talk about in a few minutes, but you would like to see the quantity x plus 3 up here instead of x, because x plus 3 appears as a quantity down here. Fine, put an x plus 3 up there, but you can't just add 3, so immediately subtract the 3. What? Why do that? Because now we need, okay, we've got the 1/11. We can just pull that out of an integral. The minus sign we can pull out of an integral. The question is, how do we integrate this kind of thing? So that's all I'm going to concentrate on now. I'm not really going to ever write the whole integral, but I want to talk about how you'd integrate this piece that we end up with. So how do you integrate, even if you rewrite it the way I say we want, how do you integrate this? And the point is, it now breaks up into two pieces that are easy. This splits up. You split this up as the integral of x plus 3 over x plus 3 squared plus 2 dx and the minus 3. So we can just pull that all the way out. The minus 3, 1 over x plus 3 squared, x plus 3 squared plus 2 dx. And you integrate these two pieces completely differently. This one, you integrate with the substitution u equals x plus 3 squared plus 2. Because if u is that, then du is 2 times x plus 3 times dx. And then you divide both sides by 2, because we don't have a 2 in the numerator. And so you get 1/2 du is x plus 3 dx. So this integral becomes x plus 3 dx, that's 1/2 du over u. It integrates to 1/2 the natural log of the absolute value of u, plus a constant, and then you put back in that u is this. So that's how you integrate this piece. How do you integrate that piece? This piece you integrate using inverse tangent. We want to integrate this. You can write this as the integral of 1 over x plus 3 squared plus the square root of 2 squared. Why do that? Oh, because from the last section, we know how to integrate. Let me switch variables. I'll use a u. We know this integral. We had it with an x in it before, but we know this integral. It is 1 over a, where a is positive, 1 over a inverse tangent of u over a plus a constant. Right? If you didn't know this, you would make the substitution that would make u equal to a tan theta. So that really means you're defining theta to be the inverse tangent of u over a. But we do know this. And so this looks like this if we would just make the substitution u equals x plus 3. If you make the substitution u equals x plus 3, du is dx, and this integral becomes 1 over, this would be u squared, and then here's the a squared. A would be 2, the square root of 2, and du. And so you'd get 1 over the square root of 2, arctan of u over the square root of 2, put back in that u is x plus 3. So that's how you integrate every piece of this. And yeah, the partial fractions decomposition was this. And you can see again how it lets you integrate the original rational function. All right, I'd like to go ahead and state the general process. I was going to do one more example, but instead I'm going to go ahead and tell you what the general process is for partial fractions, what you do in every case. It's not too hard to state the steps. Carrying them out is tedious and very long, and no part of it is particularly hard. But so there are the steps for finding the partial fractions decomposition, and then the remaining steps, or step, depending on how you count, is how do you integrate the pieces in the partial fractions decomposition. So steps in a partial fractions decomposition. So steps in integrating by partial fractions. All right. So where do we start? We assume that we've got some quotient of polynomials, some nx over qx. These are both polynomials. Of course, I'm assuming qx is not the zero function. It's not the function that's always 0. In fact, I'm going to assume that the leading coefficient, the coefficient of the highest power of x that appears with a non-zero coefficient, I'm going to assume that's a 1 so that I don't have to factor out anything. So assume leading coefficient is a 1. A polynomial with that property is called monic. It's not important that you know that. Assume leading coefficient equals 1. I want to discuss the steps in integrating this by partial fractions. So what do you do? In step 1, if the degree of the numerator, n of x, is greater than or equal to the degree of the denominator, long divide. Long divide to obtain that this rational function that we started with actually equals a polynomial piece plus some remainder over q of x, where this remainder has strictly smaller degree than q of x. All right? Of course, if the degree of n of x starts out less than q of x, then you don't have to do this step. But otherwise, you need to long divide, kind of break off this polynomial piece, and then you know how to integrate that part, so I'm just going to concentrate on this other part for the rest of the steps. In the next step, you factor the denominator into degree 1 terms and irreducible degree 2 terms. And if a term appears more than once, you group those together. So step 2, factor q of x. Into possibly repeated degree 1 terms. So linear terms. The possible repeated means that you might, this possibly repeated degree 1 terms, each of the form well, that would be a degree 1 term, but a leading coefficient of 1 would be x minus something, or if it were x plus something, r would be negative, raised to some power. So something that looks like this. This would be repeated. If m is 1, you'd just have x minus r 1 time. If m is 3, then it's when factorization, x minus r appears 3 times. So into possibly repeated degree 1 terms and irreducible degree 2 terms, which, and irreducible degree 2 terms, and I should have said possibly repeated. These two could possibly be repeated. Degree 2 terms, which, after completing the square, each of which are of the form well, you could have x minus r squared plus some positive number, and the easiest way to indicate that it's something positive is to write that it's something squared, plus something squared, and then this could be repeated. Yuck. So you do this. This can be difficult, and if there were many factors, you would just have to be given the denominator in factored form, because there's no good way to factor polynomials by hand. So you would probably be given this, so maybe it shouldn't be included as in the list of steps, but if you weren't handed it, it's what you need to do. All right. I'd like to match the numbering that I put in the book, so let me. All right. What's true is that you now write, so in step 3, you write this, we now have this smaller degree polynomial of the denominator, and we want to write that this is a sum of contributions from each of the possibly repeated factors in the denominator. From step 2. And the question is, what do these contributions to the partial fractions decomposition look like? Okay. I just want to write what they are. So suppose you have And I've just realized that this polynomial in the numerator is written r of x, and I'm writing x minus r. They are not the same r. These are just numbers. That's a polynomial. All right. Suppose you have x minus r to the m in the denominator. What is the contribution from that term? So contribution from to the partial fractions decomposition of the x minus r to the m. What you add into this sum for that is over each repeated power of that term, you put a constant. I'll explain why. Up to the power that you've got. What? Why would you do that? What's really happening is you've got x minus r to the m. And as we've already discussed, in the numerator, you ought to put a polynomial and put the most general polynomial of lesser degree than m. So a polynomial of degree m minus 1. So kind of in theory, what we ought to put up here is like an a1 x to the m minus 1 plus an a2 x to the m minus 2, and so on. The most general polynomial of 1 degree less than what's in the denominator. That is what we do, but instead of putting in powers of x, we put in powers of x minus r. So it's not hard to show that you can do this instead. So we do put the most general polynomial of 1 degree less, but we write it in powers of x minus r instead of just x. So you do this down to and so this is what you put in the partial fractions decomposition. But if you split up this sum and start canceling the factors of x minus r, this is what you end up with. And so it's just easier to realize in the first place that the contribution to the partial fractions decomposition from having this repeated linear term as a factor in the denominator is you put constants over each repeated power of a degree 1 term. What do you do for the irreducible degree 2 terms? Something very similar. Uglier, but very similar. So the contribution from a degree 2 term, which, so the form x minus r squared, possibly repeated, b squared, and then raised to the m, what's the contribution from this? Well, it's like the degree 1 terms. You get, what do you put into the partial fractions decomposition? You put each repeated power of the quadratic in the denominator up to the one you've got. And what goes in the numerators? Just a linear term, so a term of degree 1. But since we have the quantity x minus r in the denominator, every place we see an x in the numerator, we'd like to see x minus r. So what you really look for here is something like a b1 times x minus r plus c1, and a b2 plus x minus r plus c2, up to a b sub m times x minus r plus c sub m. This is the contribution from a repeated irreducible quadratic term in the factorization of the denominator. Yes, it's ugly. seriously, these days, this is the kind of thing you would definitely do on a computer or a good calculator if it were very complicated at all. But you could do it by hand. It would just take a long time. All right, that's step 3. You write this partial fractions decomposition for your rational function that has these contributions from the various factors of the denominator. Then what do you do in step 4? You clear the denominators by multiplying by the original big denominator, q of x. Clear the denominators by multiplying both sides of your equation, where you set Rx over Qx equal to the sum of contributions. Clear the denominators by multiplying by Q of x, the big denominator on the left, by Q of x, and canceling factors, and canceling. So that you end up with an equality of polynomials, as we did before. Then what do you need to do? Then you need to determine the unknown constants. So in step 5, you determine the unknown constants. This, of course, could be a nightmare if you had a lot of them. Determine the unknown constants. Either by plugging in some roots of q of x, so exceptional values. Determine the unknown constants by plugging in exceptional values for x, or by matching coefficients of the polynomials. Let me say and or, because you can mix these two as we did in that one problem. We plugged in the one exceptional value, I think it was 5, x equals 5, and that gave us one of the unknown constants, and then we matched coefficients of polynomials and found the other two. Plugging in exceptional values for x and or matching coefficients of polynomials. Great. That's step 5. So now we're assuming that we've found all of these constants, which is a big assumption because it's a long process frequently. And we've written our rational function as some sum of things of terms like this and terms like this. And we now know all of the constants. So in step 6, it's not much of a step. I would just say now we finally have obtained the partial fractions decomposition. You insert those constants back up into your, so insert the constants that you found. In step 5. Back up into this summation of contributions. That thing that you obtain, that sum of contributions with the constant plugged in, is called the partial fractions decomposition. But we still have to talk about how to integrate all of these pieces. strictly speaking, if we had to long divide it first, that polynomial piece is part of the partial fractions decomposition as well, but of the original function. All right. Where does this leave us? We have the partial, we're assuming now we've gone through these steps and we've obtained this thing called the partial fractions decomposition. But now we're claiming this enables us to integrate, so we have to talk about how you integrate pieces of all of these types. So really there aren't that many types that it breaks up into, and we can go through this fairly quickly. But one of them is going to leave us with an integral that we looked at in the previous section on trig substitutions. And then I'm just going to tell you that, and then we're going to stop. So, step 7, you actually have to integrate. I'd like to leave, well, maybe I won't. Step 7, you actually have to do the integral. The integrals. So in step 7, you have to integrate. And I'm going to tell you how to integrate the different pieces that we got. So we need to integrate things of the form, we have constants over powers of x minus r. Well, these are easy to integrate. You pull out the constant, and typically you would do the power rule. However, there's one time when you can't do the power rule, and that's when m is 1. So let me rewrite this as x minus r to the minus 1 dx. I was kind of ignoring that you need to make an easy substitution. I shouldn't ignore that. Really, you let u be x minus r, and du is dx. And I don't know why that m became a 1. I do have to do that as a separate case. Right now it should be minus m. This integral becomes a times the integral of u to the minus m du. And this splits up into two cases, when m is 1 and when m is not 1. So this is a times, and then it's a times. If m is 1, this is u to the minus 1, and you get the natural log of the absolute value of u, plus a constant. This is if m equals 1. If m is not 1, you just do the power rule. You add 1 to the exponent, and you divide by the new exponent. Let's try again. This is if m equals 1. This is if m is unequal to 1. So what does this give you? This gives you a times the natural log of the absolute value, put back in that u is x minus r plus a constant if m equals 1, and x minus r to the minus m plus 1 over minus m plus 1 plus c if m is unequal to 1. All right. That's how you integrate all of the terms that come from, how you integrate all the contributions to the partial fractions decomposition that come from linear terms. The quadratic terms, well, they're a little complicated, a little more complicated. The repeated ones get kind of ugly. So now the question is, how do you integrate something of the form a constant times x minus r plus a constant over x minus r squared plus b squared to the m? Well, in fact, this splits up into two different integrals. You can split up the b times x minus r and the c part, and they integrate in different manners. So we get, this is b times the integral of x minus r over x minus r squared plus b squared to the m dx. Yes, I left off a dx over here. Dx and then plus c times the integral of 1 over x minus r squared plus b squared to the m dx. This one is actually very easy. This one is not so easy. So how do you integrate this? As I said, this one is pretty easy. You make the substitution. You let u be all this stuff in the square brackets in the denominator. Let u be x minus r squared plus b squared. So that du is 2 times x minus r dx. We don't have this 2. Divide both sides by 2. We get 1/2 du is x minus r dx. Great. And this integral becomes the x minus r dx, that's a 1/2 du. And then it's divided by u to the m, right? All this stuff is u. U to the m and the x minus r times dx is 1/2 du. So we get this. So this is 1/2, and then it breaks up into cases again, whether m is 1 or not. This is the natural log of the absolute value of u plus a constant. I won't bother, well, okay, I will. Not the same plus c that's appearing right there. Maybe I'll call it something else. E for some arbitrary constant. This is if m equals 1. And otherwise, we use the power rule. This is u to the minus m. So we get a u to the minus m plus 1 over minus m plus 1 plus a constant if m is unequal to 1. Put back in that u is x minus r squared plus b squared. We wouldn't need the absolute value signs because that's always positive. So we get two cases. 1/2 the natural log of x minus r squared plus b squared plus some arbitrary constant if m equals 1, and otherwise x minus r squared plus b squared to the minus m plus 1 over minus m plus 1 plus e. This was if m equals 1. Why do I keep doing that? If m is unequal to 1. Great. So those cases are easy. Splitting off the quadratics with the x minus r part is easy. We are left with how do you integrate things of this form? That is our remaining problem. So we're left with these. And the good news or bad news is that these are essentially what we discussed in the last section with the trig substitution. It doesn't look quite the same. I believe that was an A instead of a B. And this wasn't the quantity x minus r, which we can fix. We can let u be x minus r. Then du equals dx. And so what you get is that this is the integral of, now it would just be u squared plus b squared to the m. I think in the last section that was probably an n dx. And the question is, how do you do this? The answer is you do it with a trig substitution. And we did it at the end of the last section. When m is 1, it's easy enough. So what does this equal? Well, if m is 1, you get just the integral of 1 over u squared plus b. dx is du. So you get 1 over b inverse tangent of u over b plus a constant. When m is 2, it's harder. You make the substitution u equals b tan theta, except really you're making substitution theta equals inverse tan of u over b. It's what we did in the last section, and if you recall, this reduces to an integral of cosine to powers, and then you use a cosine iteration formula. It's not easy, but you can do it, and I'll let you refer back to the last section. When you have high powers of m, this would be very long. Maybe it would be reasonable to have m equals 2, but even for that, I'll let you refer back to the last section. This section was very technical. The next section will be much better. We're actually going to get kind of a prelude to the definite integral, where you actually have some physical problems that we're looking at, and we want to approximate kind of what a continuous sum should mean. It won't look anything like all of this kind of awful algebra stuff.